Okay, so here we go. The first part of this is a review, so I'm going to go real quick. What I probably should have done is start with the halfway through. Maybe I should do that. All right, so you have a recording that I'm going to put up. So what I'm going to do that might be a little bit different, and maybe I'll just put up both, is that I will skip some of the beginning of this and get into sort of the newer concepts that you need to know, right? Starting with this, okay? So all the other slides prior to this have been recorded. Well, hopefully that doesn't get messed up. But I think it's there from last year anyway. So we'll just start with geometric penumbra. And you'll notice in your book you have these weird looking diagrams that take a while to figure out what's going on. It's kind of like a map, and you need the legend to figure out, that the green space on your map is a park. So on the next slide, we kind of have the geometry or the legend, so to speak, of what these trace diagrams look like. So let's go there, but we're going to mostly focus on this area in here, which is the part of this, because there's several parts, that is representative of what's known as geometric penumbra. And of course, as we should know, penumbra is bad, right? Penumbra is a blur. If there's more blur, image is worse. If there's less, resolution increases, right? So we should all be on the same page there. So here's the diagram, right? And you're going to see this in some other lectures and or chapters that kind of talk about different spots. So again, we're going to focus mostly on this. So we said it's known as the exposure trace diagram. Background exposure is represented by the height of the exposure trace. So that's kind of this height over here. And the darker the resulting image when you have more exposure. Well, that kind of makes sense, right? Subject contrast is represented by the vertical depth in the middle. That's this part here, okay? But the part that affects us the most, right, is the slope of the, what they call the edge gradient slope, but that's on the right side. We're looking at the left side. The steeper the slope, the more quickly the exposure drops off. What we want to focus on, so excuse me for the confusion, is the slope of this line right here. All right. The steeper the slope, the less penumbra there is. So we like steep. Right? Steeper the slope, less penumbra, better image, less distortion. So that said, again, we're looking at this steepness here, right? So the penumbra is represented by the gradient slope, this over here. And like I just said, the steeper the slope, the less horizontal spread of penumbra and the sharper the image. Okay, now the example. So how steep is that? That's super duper steep, right? That's like more than an upward hill, right? That's like walking up like a wall. Doesn't get any steeper. So we're getting how much penumbra there? A lot, a little, much less than C. So the reason why we're getting much less penumbra here is because in a theoretical world, of course this doesn't work in our body all the time, but the divergence of the beam totally matches the trapezoidal side here. So you're getting very little blur. Let's skip B for a second. C, how's the slope here? That's a pretty narrow slope, right? Very little. So that's going to give us the most penumbra. And we already know this from previous lectures. We've talked about the fact that a spherical object is going to have the most distortion, because there's really no, line up here. When you compare the trapezoid here, it's kind of like the line actually makes up the actual side of the trapezoid. With a spherical object, you're really just tangentially hitting it, right? You're missing things here and here. So this combination gives you this very, very narrow slope. So B is kind of in the middle, right? And there's not much you can do about this, right? It's just based on the objects in your body, right? Different parts. We're okay on this? All right. So spatial resolution is the ability to distinguish objects, really, that are in close proximity to each other. I like to say that a lot. I also like to say, when it comes to spatial resolution, the ability to resolve an object. A lot of times I'll use this sort of beach example. So when the weather gets better and we go to the beach, and we take off one clinic day because you just will only give up that one day. It's up to you. You go and you grab some sand. So if you can count the grains of sand and see the spaces between them, sort of countability, that's good spatial resolution. Where they clump together and the edges aren't well defined, that's where you're starting to lose spatial resolution. So it turns out that this picture is bad. I haven't changed it yet. Why is it bad? It's not really a good picture for spatial resolution. This is a good picture for contrast resolution, right? What would be a better picture is if we turn the red apple green, and the ability to count the apples. That's spatial resolution. So someone Photoshop this thing for me, or I have to find a picture of all green apples or something. So, to back up, and that's what happens when we kind of start in the middle, I didn't really give a good introduction, is the image overall can be broken down really into three components. So said another way, when we talk about an image and its overall resolution, we could really break that overall resolution into spatial resolution, contrast resolution, and a lot of times it's spatial versus contrast because they're hard to maximize at the same time. And then the third aspect is artifacts, which is really just, they kind of throw that in there because you don't want them, right? So artifacts just mess up images. They'll bring down spatial resolution and or contrast resolution. So when it comes to spatial resolution, we're looking at the sharpness of the image. We're looking at how small of an object that can be resolved based on a particular imaging system. And we'll talk about an example mathematically that we can figure out in a minute. But we've all used the test tools in the lab. This is an old looking one from New York. I don't know if this place still exists anymore, but we know that we can get a graphical representation of spatial resolution by using a test tool that is based on line pairs and counting the line pairs. The more line pairs that you can count, meaning the line and the space is the actual line pair. So the more lines that we can count before they start to blur together, the better the spatial resolution. We've been doing this from almost day one in the lab. Right. We're just going to kind of take it up a notch when we get into MTF in a second. And what we're measuring, we'll say that the spatial resolution is better or worse, but we're really looking at what's known as spatial frequency. So we're really looking at the number of details that you can see in a particular space. And that's going to ultimately be represented by pixels, a line of pixels. So as we've said, we're going to be looking at line pairs per millimeter. So I think we can keep going here. Okay, so this is important. And in the last class, we really didn't have much time to talk about it. So the smallest object that can be resolved, well, that's important to know, right? Because first of all, if the object cannot be resolved, that means you can't see it. And if that's a little piece of pathology, they say, I don't see anything. And you walk out and you feel happy. Right? Until things maybe get big enough to be seen. And that's not good if it's like a tumor. So this is a concept that has definite ramifications on patients. So it is said, it's not as bad as it sounds, that the smallest object that can be resolved is inversely proportional to 1/2, because I should point over here, 1/2 the spatial frequency. So what's missing here? The spatial frequency. So in order to do a problem like this, you need to know what the spatial frequency capability is of the room. This might be something that you want to know if you're in a management position one day and you want to buy a room. Do we need the best rooms in the classroom here in school? Maybe not. You don't have to spend, the maximum amount of money to get the very best equipment. It kind of depends what we're looking for. We're not going to misdiagnose anyone here. So let's take a look at a problem. All right. So what is the smallest object? These questions all pretty much read the same. That can be resolved, that can be seen, that can be visualized if you have an X-ray machine that has a spatial frequency of 3 line pairs per millimeter. So the answer is not 3 millimeters. That would be too easy. Right? The answer is not, 6 either, because that would be like a pair. 3 pairs, not really. What you need is the spatial frequency, this number 3. So let's go back for a second. 1/2 times 1/3. We're all on the same page? All right, so now it's not hard. We just multiply across. 1 times 1, 1, 2 times 3, 6. And then we divide and we find out that the smallest object that can be resolved, if you have a X-ray machine that is capable or has what's known as a spatial frequency of 3 lines per millimeter, is 0.17 millimeters. So if the object is 0.15 millimeters, can you see it? No. Is it still in you somewhere? Yes. Right? That's why we have different modalities for different things, right? Every modality at a certain point fails, though. Right? Things become just too small to see. Things get better as the years go by, and that's where maybe nuclear medicine comes in to play, where you can see things almost on a molecular basis versus on a measurement that seems small. 0.17 seems pretty good, right? I mean, but wouldn't you rather see some pathology that is on the order of microns versus millimeters, if you could? Right? I think I got an email. Another way to look at resolution, but in particular contrast resolution, is what's known as the modulation transfer function, or for short, MTF. The MTF is kind of a catch-all term. It's based on several different quality control tests. So it's usually based on something like a point spread function, a line spread function, an edge response. And they take those numbers from separate quality control tests and kind of put it all together. They don't just average them. I'm not sure exactly how it's mathematically done. But instead of finding out those specific numbers from those 3 different tests I just mentioned, they just give you the MTF. Makes life easier. And the MTF is a number range that goes from 0 to 1. Now that doesn't sound like a lot, like what's in between 0 to 1. Well, if you go by tenths of a digit, then you can say 0, 0.1, 0.2, 0.3, 0.4, until you get to 1. 1 is the best, and 0 is the worst. Now, I might as well explain it even though it's on the next slide. So I'll come back to the other one. So we're talking about the same thing. So when I mean 1 is the best, what that actually is saying is that 100% of the contrast of the actual object is transferred to the image. So in other words, the image would have the perfect contrast representing the object perfectly. This is not possible. Right? It would be great, but it's not possible. 0 means no contrast information from the object that's transferred to the image. So that's just a completely bad image, right? Maybe it's all black or all white. Something completely wrong. We can do a lot better than 0. How about 0.5? That's right in the middle. So that would say that you're representing in the image half of the actual contrast that is in the object itself. That's a lot better than 0. So we'll come back to this for a second. We are going to be looking a lot at frequency signals coming out of the patient. I don't know if you've looked at the book, but it starts to get kind of complicated, a little. When we think about data, we are going to take attenuation information, right? So different parts of the body absorb different amounts of X-rays. That will then get represented geographically, pixel by pixel, in the ultimate image. But before you get there, what the computer is doing is taking different frequencies essentially coming from different parts of the body. Usually, the smaller the object, the higher the frequency. Right? The bigger or bulkier the object, the lower the frequency. So essentially, if you do a KUB, right, that area is representative of a lot of different frequencies, some high, some low. Those frequencies are represented as wavelengths or what looks like sine waves, kind of like up here. So let me kind of spell this out a little bit. So as the line pairs become smaller and closer together, so they're smaller here and closer together, right? The rounded penumbral edges, so these parts here, right, start to overlap. So you're seeing that in section C here. When that happens, it starts to look like a sine wave. But if you ask me, they all kind of look like a sine wave. All right. So that's not as important. But when they become small enough where they're starting to overlap, and the depth of the troughs, right, which are the lower portions, right, not the top of this curve, but this part down here, this part down here, when they start to become more shallow, so vertically they're getting compressed. Can you see that? Then contrast will start to go down. Right? So here, you can visualize an object that's 1 centimeter. But here, with an object that is 0.8 centimeters, things are starting to become fuzzier and contrast starts to go down because the object is getting too small and the sine wave or the wavelengths are getting compressed and it's harder to represent as a grayscale. So we're going to see more of this in the next few presentations. And as mentioned, we can represent what's happening with our MTF. Whoops. So what we're seeing here is as the MTF gets lower, remember lower is worse, right? You can see that the spatial frequency has increased. So here's a lot of distance, it's getting smaller, getting smaller, getting smaller, and this is where we're losing things. And we're getting to the point where these line pairs are almost so close together that they're about to merge. I feel like drawing. I really wish that they had like the one after that. Right? Well, what would you expect? This number might get just a hair lower. These wavelengths here would get even closer together, and these up here might look like a solid block. And what's that mean? That means you can't resolve that object. I'll go with 3. It's kind of sort of like this, right? If you had 2 objects, but you only have 1 line pair with which to illustrate them, you can't tell. You know, unless your spatial resolution gets better and you have more line pairs, so here's another line, then you might be able to separate this into object 1 versus object 2. This is really important, right? This is how a misdiagnosis can be made. And it's not really anyone's fault, right? If the machine capability at the time doesn't allow a radiologist to see something, can't see it. So here's an example of modulation transfer function, but kind of like MTF versus spatial frequency for 2 different imaging systems. So based on this, and we'll dissect it in a second, imaging system B has both a higher MTF and a better spatial frequency. So I want my X-ray there. I have to say I had an X-ray of myself done yesterday on my shoulder by a tech who was my student, of course. That like always happens. Where? At Mount Sinai, Queens. And I gave him an A- because he had to repeat the YP. But it was nice. I skipped the line and stuff. What's that? You pulled your control back up? The YP? I didn't do it. Was it AP or did it? Oh, it was AP. Yeah. But anyway, the final product looked good. I didn't see the one that did. It disappeared before you showed. You will mess it up. Anyway, I didn't ask him what the spatial frequency capability of his system was, right? But let's take a look at this. So when it comes to spatial frequency, let's say you start at an MTF of 0.5 and you're looking for the spatial frequency. We go to system A and we go down and we get maybe like 3 line pairs per centimeter. System B, if we start at 5 again, is going to give us like around 5. That's obviously better, right? The more line pairs that you have, the better you can resolve an object. Now let's take spatial frequency. If we take spatial frequency, let's say 4, and we go up and then to the left, we see that A has an MTF of, I don't know, that's about what, 0.2 maybe? A little bit less than 2.5. If we take the spatial frequency of 4 again, but go to system B, our MTF is also higher than A because now we're above 5.5. So that we could say that this is a true statement. And system B is going to be better able to not only have better spatial resolution, because that's what this bottom part really means, but also better contrast resolution, because that's kind of what MTF is telling us. I've never had a patient ask me any of this. Even I don't ask these questions when I get my x-ray done. Because that's, how often do people even know the answer? Okay, couple more things. This, I know I'm recording myself, but this sucks. This is very unfortunate right here. So, spatial resolution is limited. The word limited doesn't sound good, does it? Because it's not. It's limited by two things. One is the size of the pixel. That's the lesser evil. So, if a pixel, the pixels are usually pretty small, right? So the pixel, or what's commonly known as the detector elements, might be 0.1 millimeters. That's pretty tiny. So the first limitation is anything that's smaller than the dimensions of the pixel cannot be resolved. That makes sense. The other limiting factor, by far the much worse one, is the actual focal spot itself. So now we're talking about stuff in the tube. The focal spot itself, right? So this is the part of the anode that is hit by the cathode ray, which is the stream of electrons coming across, is somewhere between 0.5 and 1.2. That means you cannot resolve anything that is below 0.5, even if you have a 0.1 millimeter pixel. So the problem isn't really with the pixels. I mean, maybe we'll get smaller and smaller pixels, but we are still limited by the focal spot in diagnostic imaging, unfortunately. Maybe they'll figure that out. So that's unfortunate. That means, let's say you have something that is, even with the best focal spot, right, with the lower end of the range, if we have an object that is 0.4 millimeters, like a little bit less than half a millimeter, you're probably thinking, that's almost putting my fingers together. But, that's, pathology starts on a cellular level, right? Cancer starts with a sort of malfunction of cell division, causing extra cell division, and you have too much. But if you were able to catch something with a pixel that's 0.1, and you should be able to see it because the object is 0.4, but now you're limited because your best focal spot is 0.5, then you cannot resolve that object. It's not a problem with the pixels at that point. This is unfortunate. Things will get better in time. And the last thing here is just kind of like a fact. It's also somewhat unfortunate. It's very difficult to maximize contrast resolution and spatial resolution at the same time. It's hard to get an image that has the best of both worlds. And in many cases, that has to do with what's known as the voxel. So you guys have heard me talk about pixels a lot, but I haven't talked about voxels. Anyone know what a voxel is? So let's stick with the pixel for a second. The pixel is a two-dimensional square. I mean, technically it could be a rectangle, but let's go with square. What is the element of depth on a square? None. It's two-dimensional. Every pixel is actually a voxel, which is like a sugar cube. Okay. Has an element of depth to it. Now, picture in your mind little sugar cube. Take that little sugar cube, put it right up to your eye to where all you see is a square. So the front part of a voxel is the pixel. You just can't really get the depth. In CAT scan, all right, we talk about voxels a lot because a voxel is the same thing as slice thickness. And in digital imaging, we don't talk about it that much because we don't really have slice thickness. We just have whatever we're x-raying. Like when we do a KUV, we're getting from the anterior portion to the back. Like the whole thing gets sandwiched together. Right? CAT scan is a little bit different. You can separate out the objects, kind of like a sandwich that has, lettuce, tomato, and meat, and then you can take out the tomato and isolate it. You can't do that with a regular x-ray. Everything gets superimposed. But when we talk about voxel size, think of it as a little bucket. So if you have a bigger voxel, you can pour more data into it, and you'll get a higher signal. That signal translates directly into contrast resolution. Right? So bigger voxels give you better contrast. But remember I said the pixel and the voxel are intertwined? So if the voxel gets smaller, what also gets smaller? The pixel. Right? So if the pixels get smaller, spatial resolution goes up. But if the pixels get smaller, and thus the voxel gets smaller, contrast resolution goes down. So you can't get them both to go up at the same time. Yes? No? Too much? TMI? So the voxel is kind of like a bucket, and you're pouring data into this bucket. And the bigger it is, the more data, the more signal you get. That translates into better contrast. But when you have a bigger bucket, the pixels also get bigger. If you change the size of the cube, one side also gets bigger, right? You get a bigger pixel. And bigger pixels, we said, will limit our spatial resolution, right? Because you can only image something that is as big or bigger than the dimension of the pixel itself. So you can't get contrast resolution to go up at the same time as spatial resolution. You kind of have to pick. Or reconstruct both. And then get two images. But you can't get them both at the same time. Unfortunately. So keep that in mind. All right, so what I will do, I don't even know what time it is. I will post both lectures. And even in the last one, just to let you know, let me stop recording so we don't get even more confused.